Hello, hello. Today I'm going to do a demo of semi-live coding of using Python to run a logistical regression based on a publicly available dataset. Um, if you like my videos, please subscribe. It really helps me out um, with YouTube's algorithm, and it gets me motivated to do more videos. All right, let's get started. So first of all, in the last video, we did linear regression, which was an easy concept to understand. Basically, that was just finding a line through a bunch of points so that we can predict the y value given the x value. In this particular case, it's almost same, but the outcome is different. So, for example, if your data set had these features, uh, AI people love to call them features, but really they're variables or columns. You have age, income, and gender. If you could, given the data that you were given, if you could predict whether or not a new person whose age, income, and gender you know, will he or she buy this product? Yes or no? Again, the difference here is at the end of the day, you have a yes or no answer and not a number, right? That's the difference between linear and logistic. In our data set, though, we have many columns, features, not just three, which makes it easier for the model to predict and give us better results. All right, so to do this, we're going to import a bunch of libraries. No point going over them. At some point, I'll do a video on the libraries themselves, but right now, the point is to show you how not so difficult it is to do this yourself. So I'm going to run this particular line. So all the libraries are loaded. The next step is to actually load the dataset because this dataset is already loadable, if you will, programmatically through one of these libraries. We can just call this function called load breast cancer, and we can assign them to a variable called data. So notice you don't have to go download the data or anything. It does it for you as soon as you call it. So I'm going to run that. No errors, that's good. Now, once we get the data, we're going to convert them into data frame format. Basically, if you can think of data frames as just rows and columns in an Excel sheet, right? It's a tabular format. Once you have that, training the model is so much easier. So we're going to convert them into data frames. And yeah, we're going to do that. Let's run that part of the code. And we did that. Now we're into this part of the code. Here, we're going to print just the first 5 rows of the data. You see df was the variable that had the data, which is going to run head command on that. And as you can see, there are many features / variables / columns. And we're only showing you just the first 5 rows of the data. So let's run that. And then we go to the next part where we drop the target. Target is the last column because we don't want the model to know about that because then they'll be cheating. When you do the testing, target is what the model is going to predict, 0 or 1. Does this person how likely is this person to does this person have breast cancer or not, based on all the other columns in the data set. Axis just means horizontal or vertical. In our case, this will be a vertical thing. So this axis equals 1. And we're dropping like I said, the target column. Okay, once you've done that, we're going to look at X. Then we're going to look at Y. Pardon me. And then we're going to actually look at the data set for the train. As you can see, so before that, we're going to actually do the splitting here, and you will see this command on many of my videos. It's the same, almost an exact command. What we're doing is we are saying save 20% of the data for testing and use 80% of the data for training the model. And this random state means if you don't have to have this variable in here, if you didn't have it, each time this split will be done randomly, so the results will vary from time to time. That's called variance. We will talk about that in another video. But in our case, we fix the value. That way, the results are, the split is always the same, no matter how many times you run this, and that means the result will be always the same. All right. In real life, you're not going to have that. Once you split the rows, we see that there are 455 rows for training data and 144 for testing, which is 80% to 20% ratio. And we look at the data just by running the variable, and this is 45 rows of training data that the model got, and these are the X values of the testing data, and that has 144 rows, basically 1/4 of what it had for modeling or for coaching or for training. This is the Y training data for target, which is ones and zeros, which is the result. For testing, it's not something the model is going to have access to. It's ones and zeros for the ultimate result. This is what we're going to compare once the model is run. Now we're going to actually run the model, and we're going to tell it to do 3,000 iterations. Why? Because if you do less than that, it doesn't converge. What that means is when the model runs, it checks itself what the numbers are, the results are from different runs. If the numbers are too varied, it knows that it's not doing a good job of giving you a good answer because the answers are varying too much. So once the variance is low, it knows that it got to a point that it itself at least is sure that actually is giving you consistent results. So if I did 2,000, it will see, let me just do that. If I do 2,000, you will see that it will fail with a conversion error. Well, at this time it didn't. Well, that's strange. So let's reduce that even further. And I'm trying to induce the error. That's interesting. It's not doing that. Okay. Anyway, so we've done that. So let's go back to 2000 and run that model. Now we're going to do a fitting. Fitting is basically going over the test data and actually come up with the final model, right? We're going to run that. And didn't I think it failed. Oh, that's right. If I had done 1,000, it would have failed in this particular step. So let's show you that 1,000. And now if I run the model, it should fail. Yes, yes, it does. And it says, you see, it gives you a conversion error because I didn't let the model run enough times to come up with a good prediction for itself. So run that. And now if I run this, it should not fail anymore. Yep, it doesn't. Now that it has run, you saw it took a couple of minutes, a couple of seconds. This is the predicted value of target, all right? These are the ones and zeros the model thinks it should have for those 20% of the data. So we'll run that. And now we've done that. Now we can actually even, this would be a good coaching for Jupyter as well. So I'm going to add a row here, and I'm going to look at the data, the target data, right? If I do Y, it should give me the results of the target. You see, this is 114. This array has 114 elements, some of them 1 and some of them 0, depending on what the features were for that particular row, right? Now, we can run some self-tests here to see how good the model did by comparing the results of this result with what should have been in the first place. So we run that, and you would see a bunch of metrics: precision, recall, F1 score, support. We're not going to talk about score. It's a little bit complicated, but let's start with recall. Recall means how many positives that were supposed to be positive, we called positive. And as you can see, we got 91% of them correct. And then precision is the opposite. How many were supposed to be false and we called it false? And that's 97%. So that's pretty good. F1 score is a middle ground. So you see how it's an average of 91 and 94. If your use case relies on getting the positives correct at the expense of getting some false positives. For example, if your car is driving by itself, you want to identify a pedestrian 100% of the time, even if you're wrong sometimes in terms of false positive means you think there's a person, but it's not there. In those cases, you want to rely on recall, where it's bad to call false positives like drug test. You don't want to tell somebody they tested positive for drugs when they didn't. You want to rely on the other side, meaning if you miss a few, that's okay, as long as you don't call out somebody who didn't do drugs saying they did drugs. In those kind of use cases, you want precision. If your use case is somewhat balanced, then you go with the F1 score. In our case, this looks pretty good. We have 91% precision, recall, and 97% precision. So we did pretty good. I think these are two different tests. So maybe it's an average of the both times the test ran. So you get the idea. So again, on today's video, we went over writing Python code for running logistical regressions, which is one of the easy ones to run in terms of algorithms for machine learning. I hope you found this video useful. If you did, please like and subscribe, and I will see you next time.